So then again, hello everyone. Welcome to the second talk in our actually fifth series of the EDT community seminar series. And actually, it took us five series to, for the first time today, have a talk where we will have two presenters. But before we will, I will talk about our talk today. Let me give you, as always, an overview on the talks still to come. So we have today, we have the talk by Gabriel and Cristina. And then in 2 weeks, we still have a talk by Gian from Perpetua Labs, which will be very interesting. And then to be followed by Hans van Geluwe. And one talk where we are still clarifying and trying to get a fixed speaker. And after that, as always, as a conclusion of all the talks, we will have a panel discussion with hopefully all, or at least as many presenters as possible. But with that being said, let me introduce Gabriel and Cristina, who will be presenting today about building digital twins and quadruplets. Gabriel is a professor at Carleton University and also heading the Advanced Real-Time Simulation Lab at Carleton. And he also founded several venues like the Simo Tools or Unsim conference, but also many workshops and conferences. And he's also editor-in-chief of the Simulation journal, but also part of the editorial board of many other journals. And he will be presenting today together with Cristina, who's also working at Carleton and who has, for her PhD thesis, actually won the Devs Modeling and Simulation Award, but also the Young Simulation Researcher Award already, and is also board of the directors of SES. But enough from my side. For now, I will give the floor to you, Gabriel and Cristina, and I'm looking very much forward to your talk today.
Okay, let's try to share the screen. Here we go. Okay, thank you. Welcome, everybody. Thank you for the invitation. Good morning. How do I get rid of this? No. Okay. So good afternoon for you. Good morning here. Our talk today is on building digital twins and what we call digital triplets and quadruplets. And for that, we use discrete event system specifications. As you will see, we will develop into the digital twin, but in reality, our main motivation is on the development of real-time embedded systems, cyber-physical systems. So they're everywhere these days. They have grown in popularity. Most of processors are embedded in devices like your office equipment, your cars. I'm going to turn on the laser, sorry. There you go. Home devices, robotic equipment. And the main features of these systems is that you have tightly coupled hardware with software that needs to control that hardware. And in most cases, they have dedicated function. These are not general purpose computers. I guess that everybody in this group knows that not only logical correctness is important in these systems, but also timing is crucial. And in many of these applications, we can identify criticality of the application if there is a mistake in hardware or software. The consequences are serious, ranging from extremely expensive costs up to death of the individuals, right? The community has worked in this field for 40 years now, 50. And at a certain point, a solution for trying to deal with this development problem of real-time embedded applications, formal methods were proposed. They work, they're really good. The idea of a formal method is that you start with a mathematical specification of the system of interest, and then you use that mathematical specification not only for describing and discussion, but also for doing analysis of the designs. The good thing about these formal methods is that they are provable, so you can find correct systems. They are reliable. The problem is that in many cases they are too complex. You have explosion of states when the design space scales up, and so building really complex real-time embedded applications with physical components, well, the proofs are hard to achieve, and then you end up building small parts of the application with a formal method. Another issue of many of these techniques is that they are focused on software, right? But these are cyber-physical systems. So how do we model the physical environment? None of these techniques has been created for modeling the physical environment. They have been adaptations, but sometimes they're flawed, they lack. And another thing that is very important for our lab is that besides the integration of software, hardware, and the physical environment is what do we do with the software after, right? So we want to make decisions. We want to use the tools for training. We want to use the tools for validation. And integrating a formal method with advanced visualization tools, it has been rarely done, okay? So what we have identified years ago, that there were no adequate or robust frameworks for designing these kind of systems. The formal methods are hard to scale up, but then modeling and simulation has been proposed as a good solution for solving this system. So you start with the requirements and the specification of the system, and you build models and simulate the system to understand how they work. But then here, there's a major issue because most of modeling simulation approaches are not formal. So you need to come from the model and simulation world and build models that can be mapped into hardware. This is another step that is far away from modeling and simulation. And this step is not formal, so we have lost all of the good advantages of the mathematical specification and the proofs. So this includes a new layer of work that needs expensive and costly software to be developed. And then you end up with prototyping and implementation, yet another round of different software artifacts to make this happen, right? So as you can see, the key issue here is the model continuity, because you do this with one tool, and then you do this with another tool, and then you have to code all of this from scratch, and the prototyping, and you have to build a model from scratch based on what you see in the modeling and simulation phase, and then coding from scratch. So in each one of these phases, models are thrown away. You develop everything from zero, and the apparatus in each one of these steps are different. This causes serious problems and increase in cost. And the result is that big companies will do this phase, then they will throw away the model and the simulation, and then they will start from scratch. But if you want to do this in smaller scale, this will never happen, okay? So what we have been working on, which is related to the digital twin environment that we will show later, is that we build everything based on modeling and simulation, and we develop the software applications using a modeling and simulation-based environment. We have an engineering approach that integrates different models with model continuity. We reuse the models in every single step. It's not only for exploration and implementation, and we integrate them in complex application with different hardware, different software, and 3D tools. Okay, so we will show how this is done during this presentation, but this is the motivation of what we have been working on. So this slide summarizes more or less what we do, and I'm going to go through all of the steps of the methodology quickly in the presentation. And we might need to go back to the slide, but we start as follows. We have a physical environment, and then we have some kind of embedded real-time application that interacts with the physical environment. We want to build this system of interest. And what we do, so imagine that the application is automation for comfort in an advanced intelligent building, okay? So the real-time application is the control system that will check humidity and lighting and heating and air conditioning. The physical environment is the building, okay? So we come up with the requirements for the control system. And what we do is we build a real-time controller model. And for that, we use what's called a discrete event system specification, or DEVS. I will explain that a few seconds later. We have this DEVS model, which is a formal model. And this DEVS specification is interesting because it can be used for modeling the control system as well as the controlled system. So the physical environment can also be modeled with DEVS. So our first step is we come up with a DEVS specification, and we can use formal models. We can grab this real-time system model. Through model transformation, we end up with a, for instance, time automata. We use a model checking engine, and we do formal analysis of the controller. But in parallel, if this process takes too long or the complexity is too high and there is explosion of states and the complexity scales up, we use exactly the same model for simulation. So we have a simulator that gets that model and runs simulations of specific scenarios of interest. So one team can be working on that, and the other team can be working on simulation. And we always go back to the model. Everything that we do is centered on the model. Now, as this is a DEVS model, and this is also a DEVS model, we can conduct simulation experimentation. This is where the digital twin starts showing up, right? Because we can get an environment model, and that it's a formal model that can be simulated. There are different techniques for this. Quantized state systems, cellular model, they can run in single processor in parallel for high efficiency. And we can integrate the real-time controller and the environment model and run simulations of both together, okay? If in this process we find issues, we go back to the original model and we work on the model, and we can do a spiral or even tornado development life cycle, which completes in the last step when we grab the same model and we download it into different kinds of DEVS executive that run on a variety of target platforms using different real-time operating systems or running in bare hardware. This can talk to the simulation environment as well as to the real-time controller. So it's a so once this works, we conduct experiments with the simulation, and then we get rid of the simulation, and the real-time controller is actually controlling the device. Everything is centered in this part of the process, which is the building of the model, okay? So what I'm going to do right now fairly quickly is I'm going to show what we do in each one of the steps, how we do model, how do we do environment, how do we do simulation, how we simulate that, and how we move it to the real-time executive, including the model checking step, okay? As you can see at the end, these can be used for requirement elicitation, and we can start another cycle if needed. So as I mentioned, everything that we do is centered on discrete event system specifications. Why do we use this? Well, we have been working on this methodology for over 20 years. Even before Hans presented this very popular slide in the year 2000, this work had already started, because as you can see, there are formal transformations of different methodologies into devs. And at that time, Hans identified that through what was called devs and des at that time, we could do continuous systems modeling and integrate it with discrete event modeling and do multimodal applications using devs as the assembly language for modeling. Devs and des improved into something that's called quantized state systems. So now we can have a complex application in which one component is done in Petri nets, another one is done with a cellular automata, and then you can have a subcomponent done with bone graphs. All of those translated into devs and using devs tools as the assembly language, and our research does that, okay? So, very quick definition about devs. It would take us, 2 seminars to explain what devs is, but it's discrete event formalism in which you describe what the model does using 2 types of models. Atomic models describe behavior and coupled models define structure. This is a black box model. A1, A4 are examples of that. And coupled models are white box models. A5 or A2 are examples of that. It's a discrete event formalism. That means that time is continuous. We have a continuous time base, but states are discrete. It's a hierarchical and modular system specification with an abstract simulation mechanism. When we work, we focus on the models, and the simulation engines can be built based on these formal models. And you can start with, you can do bottom-up or top-down design. You can grab a complex application and attack, complexity through composition or decomposition. An atomic model, it's not too complicated. It's defined with 3 sets, defining inputs to a model, outputs from that model, and internal states S. And these 3 sets are modified by 4 functions. One of them that tells you, what do I do if I see an input? The other one tells you, how do I generate outputs? The other one tells you how do time advances, because it's a timed formalism. And the 4th one tells you, what do I do when time passes? Okay. The one that takes input is called external transition function. The one that generates output is called output function. The one that generates time, it's called the delay or time advance function. And the one that takes internal changes is called internal transition. You define these 4 functions working on these 3 sets, and your model is built. Once it's done, you can couple them together. There's a formal specification for coupling that tells you who are your components, how are they connected, and there is a formal proof that you can find equivalent atomic and coupled models, so hierarchical composition is formally guaranteed. That was my 3-minute devs discussion. But with devs, we can do all of this, okay? And as we have an abstract simulation mechanism, we can put this to run in single processor, virtual time, real time, multiple processors, centralized, distributed in a parallel computer, or in real-time embedded platforms, okay? And we have done all of that. So let's go back to this first step. How do we define the model? Well, we can write devs models. This is a state-based notation for something called a devs graph. As you can see, it looks like an extended finite state machine. This is a simple way of defining devs models. The formal specification is more complex than that, and then you can model this in other kind of languages. But starting with that, you can do high-level modeling. In the past, we even built a SAMS VHDL interpreter that translates into devs. And we have done a Modelica tool that translates Modelica into devs and runs in simulation mode. So we have different tools for defining. You can write bare devs models, you can write Modelica, you can write Sans VHDL, you can write a devs graph like this one. And once you have this one, you can go to the model checking phase that I mentioned. So on the left, a devs model, on the right, an equivalent time automata. You can convert this one into that one, and then use well-known tools like UPAL for doing model checking on the devs model, and you go back and forth in this process. By simulation equivalence has been proven for this, so we can work on time automata and go back to and from devs. And as I mentioned, if there is explosion of states in this process, we use this for schedulability analysis and timeliness of the subtasks. So you can formally do a formal analysis of the models, and up to here we have not even thought about coding any of this. This is all formal modeling, but in parallel, we can get those same devs models and put them to run in some of the environments that we have. This is one that we have that we use for teaching and in research in the lab, which is called CD++ Builder. It's on Eclipse, and then you can run simulations of those same models while you're doing model checking. This is another definition. Here we have this is a tool called Power Devs, in which you can have continuous models defined as devs, and we can conduct simulations of the devs models in different environments. So first step, formal specification. Second step, model checking. Third step, in parallel, simulation. And as we mentioned, the simulation can be both of the model and the physical system. So I need to change the, let me see. Yeah, okay. So let me show you the video first, and let me explain you what's going on here. This is our first approach to digital twins, okay? What's happening here, as I mentioned, what we can do is we can build the real-time controller, and we can also do analysis and simulation on the physical system under study. The physical system in this case is a laboratory in what's called the Canal building in our university. We have a building information model, a building information model made in Revit for that whole building. This is that lab, and sometimes it's used as a classroom, and sometimes it's used for exams. So this was the case. So what did we do? We extract the architectural features of the room from the BIM, and we create what we see here on the right, which is a model that mimics the physical environment that we have. We have vents, okay? And the gray dots here are the vents. And we have workstations. The small dots here are workstations where students sit. And this is a wired building. So we have data for the whole year for the building. And we know what was the temperature, humidity, and in particular, we have CO2 sensors in the whole room. And we know what were the values for each one of the CO2 sensors with lots of precision for the whole year. The building is a live lab. So what happened here is that my student came, and what she did was she was a TA for a midterm. So she collected who was sitting where, when did they come, and when did they leave, and then she built a simulation model of CO2 in that building. So we extract the features, we have the simulation model, and we have the CO2 embedded controllers built as devs, all of them integrated seamlessly in a simulation model. Now, next step is we could control those CO2 controllers, and for that, we have what's called real-time devs and real-time cadmium, and we have tools that run on embedded hardware. And based on this, what we have built is what we call a digital quadruplet. Here, what you have is another lab. It's a beam of the lab, okay? And then this is the data extracted from the actual building. So we have the room, we have a model of the room, and we have built a physical model of the room, all of them connected through a devs model. And what we can do is experimentation on this physical model that has exactly the same sensors that the room has, and do visualizations on the physical twin, digital twin. And then we have this physical component and we can integrate all of them. We do that through, so we start with a BIM model, we integrate it with a simulation as I showed a few seconds ago, and then we see the results on a virtual model or a physical model, and eventually on the actual room itself. We have a large set of BIMs on campus. We have done work in converting 2D geometry into 3D buildings. So we have done work on Revit, and we have lots of information on, we work with the School of Architecture, and we have detailed floor plans for the whole campus, and we can conduct experiments with this, integrating different visualization tools, okay? And this is how it looks like. This is one of the buildings. We have all the building in detail with the vents. We extract the vent data from there. We build the digital quadruplet, and we conduct experimentation, okay? So one of our examples of use of the technology that we have developed is on building automation. But we have an ongoing project with the National Research Council Aviation Lab. And what we have been doing is working on a digital twin and real-time control of a supervisor of a helicopter. So now Dr. Ruiz will explain the details of this project. Yes, and I will let her continue from here.
Okay, thank you so much. So I will continue explaining the details of our project to control a helicopter for autonomous flying with following this methodology. And as Dr. Wainer says, it's a project that is ongoing with the National Research Council. So what we did is follow the exact same methodology that he just presented. And I will not go into the details of the models or the implementation. I will just explain you how this follows the methodology and what we did exactly. So first, we need a supervisory controller to control the helicopter because it has many components. Let me go a little bit ahead and show it to you here. So basically, in the helicopter, we have an aircraft that has a different states that will provide telemetry. We will have a flight control computer, we will have a display, we will have perception system, we will have to manage the mission and so on. So all these components needs to be controlled. So for that, we develop a supervisory controller, and this controller is developed using the desk formalism. So what we focused was on the landing phase, and now we are extending that to other phases of the flight. And as you can see here, we have a desk couple model. As you can see, we have our boxes there with our inputs and our outputs. And then each of these boxes is developed as either this atomic model or this couple model. I will take a look at one of them. For example, here, that is, no worries, that is this atomic model. And we will follow the depth graph notation that Dr. Wainer explained a little bit. So I will go a little bit more in detail there. So we specify the states as bubbles, and inside each state we define the time advance of that state. And as we mentioned, in depth, transitions between states are defined either by internal transition or external transition. So we define the external transition with thick arrows, and we define the internal transitions with those arrows. In the transition that define the, in the arrows that define the external transition, we define what are the possible inputs that we can receive in the input ports. And based on that, we decide to which state we transition. And when we have an internal transition, the internal transition is associated with an output. So we specify in which output port we generate the output and which output we generate. So having the model defined in this way, it was very useful for that, because on top of being able to do model checking, it was a easy notation and a graphical solution that we could share with the experts from NRC, and they could validate the model before moving into the implementation. So when we define this, we share with NRC, and we have back and forth in our designing process. And once we were happy with the model, we could move into the implementation. So basically what we did, we implemented each of these models. And for the atomic models, what we did was white box testing. So we developed the possible transition tree, and we test this model in simulation to make sure that all those transitions happen as expected. And when we were having each component ready, we were coupling them together, and we did integration testing until we were satisfied with the model. Okay, so with that, everything was run in simulation, but this supervisor needs to work on real time. And as Dr. Wainer said, our methodology, in this, we have engines to run the models on real time on different platforms. So what we did is we ran this same supervisor controller in real time using Linux machines and Mac OS, and we test those providing inputs to the supervisor and making sure that it behaves as expected. But as an aircraft is a critical system, so we cannot rely just on that testing and move the supervisor to the aircraft. So we have our supervisor, and it is fully tested, and we cannot directly move to the aircraft. As you can see here, there are different components that the supervisor needs to interact with. It needs to send outputs, and it needs to receive inputs from that component. So basically what we need to define is an interface, and we define that interface using also this model. And in this case, we follow the UDP communication protocol because it was the one that was used in NRC. In the current phase of the project, we are improving this communication protocol to have a reliable one. But the important part of this methodology is that this supervisor that we have defined will not be touched. The only thing that we need to modify are the interfaces to ensure reliable communication. So when everything was done, in NRC, what they have is a digital twin of the aircraft. So here you can see how the different components are in the aircraft. So we have the Mac Mini with a supervisor, a mission manager, and ground control computer. And then we have the aircraft, flight control computer, a display, and the perception system. But what they have is a digital twin where all these components are in a single machine. So they have a model for the aircraft, for the flight computing, from the display, and so on. So we integrate it in the digital twin, and we test our supervisor with the digital twin before moving into the aircraft. So that way we show the whole development process where we define the model, simulation mode, model checking, then real time with a fake environment, real time with a more realistic environment defined with the different model for the different components defined by NRC. And these were just software running on their own, and we implemented our interfaces to connect them, and then we deployed on the aircraft. So here we can see a video of the helicopter flying. Not all components are developed by us, but the supervisor that controls how the components interact with each other and says, okay, now you can land, or we have found a point where it's safe to land. This is done by our model that was developed using this methodology and tests. So here you can see how the helicopter is landing, and this landing phase is controlled by our supervisor. So I will head it over to Dr. Wainer, so he can do the summary
Yeah.
of the presentation.
So yeah, in summary, as you can see, what we have is we start with the requirements of the real-time control system and the physical environment. In the first example, what we need to do is to study the amount of CO2 in a room, and we need to control the airflow in that room based on the amount of CO2 in the room. So the physical environment is the room plus the individuals and the CO2 that they emit, and the controller is increasing or decreasing air conditioning or heating with particular emphasis in the ventilation to have clean air. In the case of the helicopter, it's so you have an autonomous system. The autonomous system is connected to radar, landing equipment, etc. There are subcomponents on that, and there is, so the physical environment is the helicopter, and the weather around the area. The supervisor requirements are all of the steps that are triggered according to different conditions. So we can model the environment and we can model the controller. We use devs for that. And if there's a better tool, we can do, if there are components that are better done with, let's say, Petri nets or state charts, you can do them with state charts and convert them into devs. Once converted into devs, we can do model checking of them. And once we have the model, you can simulate them using the abstract simulation algorithm. You can also simulate the physical environment. I showed you the CO2, and the digital twin has the physical environment is the helicopter. And once you have tested everything, the same model goes into the real-time executive. In the digital quadruplet that I showed, it's controlling the room, it's controlling the maquette of the room, and it's connected to the BIM model that shows how it's being used. In the case of the helicopter, there is a board that is used for simulation first, and in the helicopter itself that executes the supervisory system. And using this methodology, so that helicopter controller has been done by undergraduate students, right? This is not high-level PhD research. This is at the engineering phase. What the PhD and postdocs work on is all of this slide, but once you have the methodology developed, this is simple to do even at the undergraduate level. In the end, we end up having a model-based engineering technique for developing this software. We use different types of hardware, different types of software, and we have 3D visualization engines. You reuse the models throughout the process. So the students that are continuing with the helicopter this year, they are building new stuff based on last year. And there's real reuse. It's you get a box and you can reuse them, and you end up having a collaborative environment with advanced visualization. You can use it for serious games, training, and testing, verification and validation of the application. And that's all that we have. We want to thank many of the students that participated in some of the things that you saw in these slides. And that's all for today. We have our YouTube channel with videos of the stuff that we presented today, our website, and we have a Twitter feed. And thank you very much.
Thank you very much. Let me give you a round of applause. I'll also try to do that physically. Well, thank you very much. I will stop the recording for now.